Welcome to the lecture for double angle formulas. Double angle formulas are easily derived from some formulas, and because it's so easy, I'm just going to do it right here. Unlike in the last lecture, I just relied that you look at the proof in the book and didn't bother with doing it. But this one is so quick here. For example, we can say that since sine A plus B, and this is a sum and difference formula, is the same as sine A cosine B plus cosine A sine B, that when we let the two angles be equal to each other, we come up with sine A plus A, and then of course this is an A, that's an A, and then what we have is that we come up with sine 2A equals 2 sine A cosine A, just like it says for the double angle identity. Really similar for cosine of 2A. We encounter the peculiarity that there are three of them that arises from the fact of having the basic one, cosine squared minus sine squared. When you use the Pythagorean in here, either substitute for the sine squared, you get this one, or substitute for the cosine squared, you get this one here, and that's kind of why we have three of them. Again, just like the sum and difference formulas, be familiar with the double angle formulas, but instead of memorizing them, just know where to find them and how to use them. So let's do a few examples here. I'm going to try to keep these available here. I'm not sure how viable that will be, actually. I think I just paste them in here and scroll down. There we go. All right, proof that sine theta plus cosine theta in parentheses squared is the same as 1 plus sine 2 theta. I'll start with the left-hand side. So left-hand side, let's see, I think I just rewrite the whole thing. And then what I have here on the left is perfect square trinomial, sine squared plus 2 sine cosine plus cosine squared. So that's what I'm going to do. Let's see. Of course, I need a little space here. There will be a times now. Let's see if I can get that from somewhere. Apparently not. So there we go. There it is. There's 2 in between, and then this one will turn into a square. Here we go. And we have a square here. Okay, got it. Now on the left-hand side, I see that sine squared plus cosine squared equals 1. So I'll write that down. So it's going to be 1 plus, and then this one is inside that. Well, and at this point, we're done because we can see that this is indeed a double angle formula right here. 2 sine cosine equals the same as sine 2 of the angle. And of course, there's a 1 in the front of that. So with that one, oops, okay. That is the word done in Greek. There we go. Looks better. So here pretty much what I did for these was FOIL, and then what I did here was Pythagorean. There we go. Okay. Show that sine 2 tangent is the same as 2 cotangent over 1 plus cotangent squared. I'm going to operate with the more complicated side. So I'm going to get cotangent into sine over cosine over sine. So this one will turn into a fraction. Sine x over, whoops, cosine x over sine. And this one down here will be a square. Okay, let's see what happens next. I just have too many fractions floating around, so we'll be multiply all terms with sine x. That will work. I did here in between is, of course, ratio identity. Okay, so I'm going to do this one here. There are just too many denominators floating around. How do I get rid of the denominators? Well, I multiply everything with sine squared. Oh, so what I just mentioned a moment ago, that actually means sine squared, not just sine. That's because of the second denominator, this one right here. So multiply everything with sine squared, which means in the numerator we have 2 sine cosine, as one of the sines cancels. So we have 2 sine cosine. And in the denominator we have a sine squared here. So we multiply with sine squared, and of course we get rid of it right here. So we have a simple cosine squared there. Okay. At this point, the denominator equals 1 because of the Pythagorean, and therefore the numerator equals the left side, which is the double angle identity. And we're done. We may want to write this down correctly, but if we explain it, then we're fine with that as well. We just want to get it as far as we can and then explain the rest. Okay, next example. And by the way, I will do one more example here, and then I will stop the lecture, and then the very last one here, this one here, I will do later on. Okay, so let's do this one. Let's have a little space. The book that I'm using is manipulating the cosine 4x on the left-hand side. And they know where they want to go with that. They want to go with double angle formula for the cosine. In fact, let me get this down here. I insert it in here so we can look at it. What I want to do instead is adhere to what we have learned, look at the more complicated side. And the more complicated side is, of course, on the right-hand side. It almost looks like a perfect square trinomial, but not quite. If it looked like the following, watch this. Now we could say, hey, that factors into 2 cosine squared minus, no, that's, yeah, minus 1. 2 cosine squared minus 1 squared. Unfortunately, it doesn't look like that. It doesn't have 4s, it has 8s there. So what I'll do instead is I'll use a little trick. I manipulate the right-hand side to make it look like the perfect square trinomial. In order to do that is I factor out a 2 from the first 2 terms. So I have 2 times 4 minus 4 parentheses. Okay, looks the same, right? So far so good. Now what I do is I transform that 1 here into a 2. Ooh, that sounds weird. I cannot really do that, but I can do this. 2 minus 1. Same deal. Why do I want to do that? Because I want to take this 2 on my next step inside here and actually make it that desired perfect square trinomial. So let me show you. So I take the 2 inside here. Of course, when I take the 2 inside, I factor out a 2, which means actually I'm just taking a 1 inside. Now what I have actually is this perfect square trinomial here inside, and that's where I'm going to continue with. So try to get the right-hand side try to transform the right-hand side into a perfect square trinomial. Okay, which is what we did. Part of it, at least. So now we have cosine 4x equals 2 times 2 cosine squared minus 1. So I'm going to use this one here. 2 cosine squared. And then I think I'll borrow 1 right here, minus right here. And that whole parentheses is squared. And then I still have the minus 1 here in the back. Okay, here we go. Was it worth it to do that? Well, yes, I did log out. That is the second double angle identity for the cosine. So what I have here is 2 cosine squared minus 1 in the parentheses is the same as cosine 2a, or cosine 2x. So this one right here is this. There we go. So here I used a double angle identity. Okay. I kind of knew that ahead of time. Actually, I was looking at the example in the book, and that kind of guided me towards doing this to the more complicated side. But I was also kind of thinking, gosh, you know, there's supposed to be an identity. I'm looking at the complicated side. It almost looks like a perfect square trinomial. Let me just try it and see what I come up with. And indeed, not only did I log out, but I had to log out that I came up with a double angle identity, because that's what we're supposed to do. Okay, how do we go on? Well, we're actually done. Notice that this one here is exactly another double angle identity for the cosine. In fact, it's the same one that we had. So this one here is the second double angle identity for cosine, and this one is again the second double angle identity for cosine, and we're indeed done. Oh, I did make a mistake though. I did make a mistake. Right there. 2 cosine squared minus 1. That becomes from the identity cosine 2x. I forgot that 2 there, right there. And now this 2x here squared, 2 cosine 2x minus 1. Now the a is 2x, so a is 2x, comes on the other side to 4x. So that one here I kind of overlooked at first, but I just corrected myself. With that, I'm going to interrupt this lecture, and in the continuation I'm going to go on with the last example that I have. Okay, welcome back to the continuation of this section on double angle formulas, and this is what we're supposed to do. If x equals 3 tangent theta, write this expression theta over 2 plus sine 2 theta over 4 in terms of x. So what we're supposed to do is to write this as a function of x. And let's see how we can achieve that. Well, what we can do is we can take what we have originally here and say that theta equals inverse tangent of x over 3. So I'm just going to write this down. Theta equals inverse tangent of x over 3. I think I put this in parentheses, and that of course is the inverse tangent. Okay. Well, we can do that, and then just plug it in. But they want to have it a little bit more complicated. In fact, over here, what would happen is that we have sine to tangent, inverse tangent, then we have an inverse tangent inside the sine. That's legitimate. It just looks somewhat ugly. So let's see what they want us to, how they want us to coax into, whatever the English is, and we should be coaxed into doing certain thing here. So I'm going to take this one here. Sorry about my English there, kind of left me. I'm going to use a double angle formula on this one here, which of course will come out to sine theta cosine theta cosine theta. There we go. And actually that is 2 sine theta cosine theta. Okay. Now, and then of course, I should also say that, well, one of the 2's cancels here, so I have a none here, and then I have a, if I ever get there, I have a 2 in the denominator. Okay. Now what I can do is I can say, well, I don't know what sine theta is, I don't know what cosine theta is, but I can look at this triangle here and say that if tangent of theta is x over 3, and then of course the hypotenuse, when you calculate it, comes out to square root of x squared plus 9, then I can use that, and then the sine is going to be x divided by that hypotenuse, and the cosine is going to be 3 divided by that hypotenuse, and that's what I'm going to use. By the way, a little thing on the side here, I just want to do this particular example for completion of the section, but you will not encounter it on any test. Okay, so let's put in this fraction here. So for the sine, we have x divided by the square root of x squared. When you look at my drawing, you might be able to detect it took me a while to actually draw that, to actually write that in Paint. And then that's that square root symbol there. And let's see, and then for the cosine, that looks like this. And here for the theta, I actually used the original inverse tangent of x over 3. X over 3, there we go. And now I combine a little bit here. Especially the second fraction here, will become an x squared plus 9 in the denominator and 3x in the numerator. So there we go. Oh yeah, get rid of the whole thing here, and then just a 3 right there. And then I guess we can figure out a 1/2. So I'll do that. 1/2 times, put everything else in parentheses, without that the denominator of 2 is already gone, plus this one here. And there we go, and we're done with this one. Looks pretty complicated, and it was just an exercise of doing something like that. Okay, with that one I conclude this lecture on double angle formulas.